sorry, I've seen this. Today I'm going to be doing a Rosalind problem. I haven't really tackled this kind of problem before, but I have seen this method of representing DNA, well, in some of my bioinformatics material that I've looked at. And so basically what we're going to do is we're going to take a certain number of DNA strings and compare where they're the same and where they're different using a profile matrix. And I'm not really sure how to do matrices in Python, or at least I've never intentionally done matrices in Python. Thinking back on it, I did a project with 2048. I made my own little 2048 game, and I didn't know what I was doing at the time. I didn't know that it was related to matrices, but I think it kind of was, because I was taking the rows and columns and splicing them up in certain ways and adding the nth item from each row. So hopefully I do actually have a little bit of conceptual understanding of what I'm supposed to do here, but we'll just have to see if that actually plays out in reality. So let me take you over to the desktop and I'll show you what we're trying to do here. I'll try to explain it the best I can. So the problem on Rosalind explains it better than I could, but basically we're going to be taking strings of DNA of the same length and putting them into a matrix, and then we're going to count nucleotides at this certain position, first, second, third position, and basically sum up the amount of ACs, Gs, and Ts there, and see if we can, excuse me, trying to figure out my gain setting here, see if we can basically get an input FASTA table and output something called the profile. And I'm kind of looking at this. If you see here, we're looking at the first position, and we're supposed to run it through our script, whatever our script ends up being, and we're going to count 1, 2, 3, 4, 5. There should be 5 A's. There won't be any C's. There's no C's in the first position of any of these strings. There's 1 G and 1 T. Yeah, 1 T here. And then we're going to be doing that for every one. I've never done a problem like this before, not specifically like this. Put this in full screen. So this is going to be a new experience for me. And we're given a sample data set, so that our file will look something like this. It'll be a text file, and we're supposed to have, this is the sample output, so we're going to have to make it look pretty much exactly like that. Whew. I'm a little bit intimidated. This is definitely going to be the most difficult problem I've taken on from Rosalind, but we'll see what happens. So my first thing is I want to make a text file in here. Let's just copy this one. Let's rename it. Oh, let me put something soft under my keyboard. I'm going to try to just work on this for about an hour today, because I want to go for a walk before I go to bed. And I want that walk to be about an hour, so that's how much time I have. So if I don't get it done today, I will probably make a part 2. Have another go at it. So let's practice, what were these things called again? It's a problem if I don't know what they're called. Consensus. Okay, then we're just going to open that guy up, delete what was in there before, and then let's copy this in there. So now we have something that we can run through our script and hopefully get the same output as this before we try it with the real deal. So now we can make a new Python file here. I'm going to save it as consensus.py. Okay. So let's kind of try to outline. I'm going to try to make a game plan, so I'm not going into this super, without any idea of what I'm going to do. So if the first step is obviously we're going to have to. Step 1 is going to be read FASTA file, and then from FASTA, I'm not going to put step numbers in there, that's dumb. Read, and let's also just do so we're going to have to read the FASTA file. Next, we're going to have to format it and make a put information into a matrix. Let's call them homologous genes. And homologous genes are basically genes that you get from a shared ancestor with another individual, whether it's a cow or a cat. It's going to be a similar gene probably if you're closely related, with only a couple differences. So we're basically looking at different homologous genes. And by the way, homologous genes, I don't know if you could stretch the definition to say like it's a homologous gene between you and your sister. I guess you probably could say that, but you're just taking the same genes from two different individuals and looking for differences. So we're going to take homologous genes and place them in a matrix. Okay, then we're going to go through the columns. And sum the nucleotides of each type. Okay. Then that will go into a list. And we're going to have a list of nucleotides in each column. So it's going to basically maintaining the columns, I think, maintaining the columns. It's going to be and placing them into a new matrix. And forgive me if the terminology here isn't professional. I haven't been trained in this. I'm going through this as a complete beginner here, so I don't really know if what I'm saying is totally correct here, but I'm trying to get there, at least conceptually. So we're going to go through each column and some nucleotides of each type. Placing the value into a new matrix. Let's what was it called? Profile matrix. Okay. And then finally, return the results. Okay, so that's the broad strokes. Sorry, I'm gonna one last time make sure something doesn't sound right to me. Okay. Okay, it wasn't on the right setting on. Sorry, technical difficulties. Okay, I wasn't on the right microphone setting, that's why things sounded strange for me. Probably for you too, but you probably cared less. Okay, so that's the broad strokes, and then we're going to go in to each of these individual steps, and there will be smaller steps, obviously. So I'm trying to think, first of all, how do I want to approach this? Do I want to go at it with file open? I don't know. I think I'm just going to, I'm not going to do that. I'm going to, yeah, I'm going to put the contents of the file as a variable, and then I'll have to close the file at the end of the script. Not that I necessarily have to for it to work, but apparently that's something you're supposed to do. I don't know why, but I remember that being a thing. Okay. And we're just going to open this FASTA file to read it. So file equals open whatever I named the file, practice consecutus.txt. I don't need the full file path because the Python file and the text file are in the same folder. Okay. And we don't have to say the read is the default value. And contents. Okay, so let's see. Print file contents. Oops. Okay, that doesn't look right. Oh, I need to save this. Let's try that again. Okay. So we've read the file. We don't need the tags here, so let's do some splicing here. Will that do it? Nope. File.read print contents. I want it to only read every other line. I learned this a week ago. I should know. Okay, let me pull up some help here. Nope, I'm going to try to figure it out without the help. Let's do Okay, so it's going over things one at a time. Read lines, I think, is what I need. Okay. So now we want to, starting at 1 in steps of 2. Okay, so we're starting at so the 0 index number will be the titles, because that's the first thing. So we want to go starting at 1, going in steps of 2. These are our individual strands. Okay. Let's call this okay, so we're going to make this a tuple, I guess, and then a tuple of lists, and each list will be a row. Okay, and also we need to keep cleaning this up first. Okay, we're just going to make this into a list of strings for now, first. For line, print line, and instead we're going to do lines, line equals line dot rstrip. Let's see if that's what we want. I don't think that is. I think we want to keep the new line characters for now. Okay, no, that is what we want. So now we have a list of strings. And if we want to print that to look like a matrix, we need to do another for. Okay, so this is what we have. So that's going to be our first column, second column, third column. And then since these are all going to be the same length, we'll know that we have the length of this, that's going to be how many rows we have. That's a matrix already, because we can just label these row 0, 1, 2, 3, 4, 5, 6, and so on, depending on their index number, and then iterate through the list items. And then to call the columns, we can just use list splicing, I think. So that's that. Let's say print have another idea to make this a little easier on myself. We'll have a counter at 0. Should I make the X values letters or numbers, or should I make them both? I think I should make them both numbers in this case. So I don't have to make a dictionary with the entire alphabet, especially since I don't know how long these are necessarily going to be. It could go beyond 26. So I'm going to use a 2-number system. Count X for the rows and count columns. Sorry, count X for the columns. Count Y for the rows. So first we're going to do for I in range length of strands 0, could be any. There we're going to say for I in and then we're going to have like a, let's call this one X label. We're just going to keep this nice and simple. It's just going to be an empty string. X label plus equal I. Count X plus equals 1. So it's gonna hopefully make a new string here, and for every new character it sees in the first item, in the first list in strands, or is it a list of lists? I think it's a list of lists, which is fine. Doesn't need to be a tuple. I think it can be a list. We're not going to have to change it, but yeah, it doesn't matter. I don't think it matters anyway. So it's going to go through each of these and put a 1 above this, 2, 3, 4, 5, 6, 7, 8. Actually, it's going to put a 0 here because we're working with list slicing, and I think zeros will be easier so that I don't have to do any mental math. Okay, so and then we're going to, at the end of it, print X label. Does not like it. Plus equal 1. Oh, I was right the first time. Just want to add a string. Print X label plus equal string version of I. 0, 1, 2, 3, 4, 5, 6, 7. Perfect. So now we need to find a way to do that on the y coordinates of this matrix. And let's put a space here because reasons. Let's put 2 spaces here. Okay, and reasons that hopefully will become clear in a second. So now we're going to go do the same thing basically for each row in the matrix. And let's keep this one empty. Then for I in range length of string, and we're going off of the length of the list that's containing the list, so the length of rows, the number of rows, for I in range, which is going to be length of the strands list and not an item in the strands list. I think this is going to be basically the exact same thing. Okay, the difference is we need to find so what I want to do is for each row could do another excuse me. I think the better way to do this would be to actually incorporate this into here. That's supposed to be Y. Oh my. Do I not have the same Control-C, Control-V? Because I'm already iterating through it here, and this way if I build the Y label as I'm going through here, I can use the same counter. Count Y plus equals 1, and then we're going to move our print statement up and print F count Y strand. Do I have a count Y? I don't have a Y counter yet. Or maybe I didn't, I deleted it, I don't know. Let's see if that works. 1, 2, 3, 4, 5, 6. Works beautifully. So now we can just look at this, and see our labels for our X and Y axes and how to access them with strings. I mean splicing. So this is a little code that we can go by. Oof, my brain's hurting. This is going better. This is going much better than I thought it would, though, so far. So we can check these off. Now we need to find a way to comb through each column and sum the nucleotides of each type, placing the value in a profile matrix. And this is I guess this is the meat of it now. So I need to go through the index numbers. Okay, I'm kind of seeing what I need to do. I'm wondering if it would be easier to do a function for this. I mean, this could all be put into a function. Maybe I'll do that after I have the logic at least figured out in my head. Sorry, I'm thinking real hard. For value in range length of row, which is basically the same thing as this guy right here. We comb through our rows again and count the A's. We're going to need to make a new matrix. Okay. We'll call it profile. I'm going to look at the example again. ACGT. So I can make I think the easiest thing to do would be to make a function to count whatever nucleotide you want in your row. I think I will make a function for this. What should I call it? Row column count? Nuke column? I don't know how imaginative that is, but it will work for now. So I'm going to need to feed it an index number and a nucleotide to look for. Index and nuke. And I think I need to feed it also a matrix. We want to extract from it a list. No, do I want it to be a list yet? I don't think so. I think I'm going to get this smaller. Oh, my brain hurts. This is physically painful. Okay. It might be easier for me to draw this out, but I'm going to stick through it because I don't have a way to show you what I'd be, well, I do have a way to show you what I would be drawing, but not a convenient way. Okay, let me write it down. Use index to comb through each column in a matrix at index position. Count given nucleotides per index position. Return a row with sum of nuke at each position in range length of row. each position in the row. Okay, so I'm going to need a counter to give us what index number to start with. Then we're going to iterate gonna mute you real quick. Okay. For row in matrix, and then for I in row, I don't need that. Do I? For row in matrix, and then for I in row, I do need a counter. If I equals given nuke count plus equals 1. And I don't think I need the index. Yeah, I think I'll call this after I use the index somewhere else. So, and then we want to return count. So now let's try nuke column A's in just call it A's in matrix strands 16 A's. That doesn't seem right at all. 1, 2, 3, 4, 5. That's because there is only, I do need an index. And then for row our problem. Row is not defined. Do you mean po? For row is defined. Maybe I can't splice. No, that's probably the problem. Okay, 5 A's. 1, 2, 3, 4, 5. Okay, that worked. So now we can call this function later. We're going to need an index counter. This is getting messy. So that works. Let's try it for the next row and column. There's 1A in that column, correct. Okay. I'm going to move this function up to the top so it's not in my way. It's kinda making things look messy down there. Okay. Print X label, that needs to stay here. So we're going to need to call that function 4 times for each column. I'll be right back. I'm back. Okay, where was I? For strand and strands. Use an index number to comb each column in matrix at position. For each type of nucleotide, use an index number to comb what was the order that they had it? ACGT. For I in range, length, I'm going to make a quick change here. Column length equals see, because I'm going to have to put that in a couple places. Does everything still work? Come this out real quick. List index out of range. Okay. In the range of the column length, for I in range of column length, and that's going to be our index. No. Maybe. Okay, let's not try to do this all at once. Let's keep. Okay. Think. per Newton, HCGT for I in range column length. Newt count. I don't have anything else named that yet, do I? Newt count equals an empty string. Already have that part done. Wait, no way. Is that it? Oh my gosh, I can't believe that worked. Oh man, that's I didn't think that would work. It just worked. It is the highlight of my day. On my janky ass code that I'm. Oh my gosh. Okay, so you can see that this matrix over here is identical to this matrix. I'm gonna go through. Okay, so now I can do my little F string thing here. Nucleotides base new count. And where was this one coming from? There, I don't need that. Can't believe that worked. I cannot believe that I made that work. I feel like it's pure luck almost. Why did I get 2 new lines? That made my whole day. I'm not even kidding. That just made my whole day. And is it in the format that they want? And they want the output to be ATGC AAT consensus. Oh, okay. There's one more thing that I have to do. I go through this matrix and decide which one there's the most of. Okay. Man, I cannot believe that worked. So can I go and just I need to go through each column again. Okay. Okay. I'm not quite done yet. So that is the consensus. What is prof? What did prof even stand for? Oh, that's profile. Okay. So I need a function to find consensus. I'm almost out of time. So I'm going to go through, I think what I'm going to do is I'm going to do basically what I did up here and find, maybe make a new list and then just return the maximum value of that list. I think might be the easiest way. I don't know if I want to make a new list. I think I might do another way to find the maximum value. Column length max max equals for range, I in range, column length. No, that's not what I want. This is getting difficult. Yeah, okay, I think I do need to make it into a new list. Okay. Then I need to keep track of, I need to find the index number of the max value. And then index 0 will correspond to A. 1 will correspond to C. G will correspond to 1, and T will correspond 0, 1, 2, 3. Okay. Def consensus matrix consensus equals we want this to be profile, which is a matrix of sorts, I suppose. So I need to think of these in terms of index numbers. So I could take the first index and put it into a new list, and then find the index of the maximum value on that new list. And if the index is 0, return A. That seems like a way that would work. Would that be the best way? I'm trying to think of another way. So our output's going to look like this. Go index. And it doesn't have to be an index, I guess. I guess it should be a string, yeah. So we're going to go through each row. I'm going to say I think I used up all my brain juice already. Flip list. No. Is that a good way to do that? Would it be best to turn this into a dictionary? Oh man. Okay, clearing my head. Yeah, I think this is as good a way as any to do it. That's at least the only way that I'm thinking up right now. So for I in the range of the column length, and then for okay, I'm just gonna make a consensus max and column. Max and call. So we're just breaking this down into one step. Can I do that? Can I do that? Max. Can I return the index? Can I return the index of the max? Maximum value. What does that even mean? I think that's probably what I want to do. But I'm going to try to do this in a different way. Probably not as good of a way. say if row I is greater than the max, max equals row I. And for now, let's just do print max. Column. Where did I add a space there? Huh. I don't know what happened there. Let's try the consensus of prof. I spelled consensus. I don't know. For I and arrange the column of the, and for row and matrix, if row I is greater than max, max equals row I. For row in matrix, it should be here. Okay, so one problem is I don't actually have this matrix built yet. I just have this printed out here. So I need to build this. This is getting weird. So I haven't actually built this into a matrix yet. It just looks like one. Oops. You don't want to do that. Okay, so I've got it into an actual matrix now. I can keep this part because that's how it's supposed to be formatted. Okay. Okay, so here is our matrix now. So it looks like it successfully found our maximum value. not supported between instances of string and integer. I don't think that was our problem then. Max equals integer row I. Maybe that's it. Oh, that's a lot of numbers. 5. Why are we getting all those? Oh. There we go. Consensus. So that's the max value of any integer in the entire matrix. So that's not really what we want. But I think we're on a good track there at least. For I in the range. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Five, 5, 6, 4, 5, 5, 6, 6. Okay. So this gets the max number in a column. Oh man, it's time to be done. Let me put a little note. trying to identify the most common nucleotide in the profile per column. I think I come back to this tomorrow with a fresh mind. I'm going to come up with a solution pretty quick. I hope so. And I don't really think it's going to be this solution, though. I think I'm going to have to put each column into its own list so that I can keep track of the index numbers. So I'm going to have to turn, basically, I think I'm going to have to flip this thing, mirror it along as like a central axis here. That's what I did in 2048, if I remember right. And then we're going to have 4 columns now. And then the max number in that column, I think I can actually use this. Find the max number in that column and associate that with a TGRC. So I think I do need to flip this. I think I might be able to use this function though somehow. But we will see tomorrow or whenever